Yes.
When I was preparing my answers, there's like a ton of different ways you could write. Like,
Yeah.
we were finding the domain.
Uh-huh.
We were writing it on the board like negative infinity, comma, negative 4. Like
Yes.
But in the book, like, it was simply x so that x does not equal whatever your...
Yeah, there's different notations. There's set notation. There's interval notation. I want you to do interval notation.
Okay.
I think interval notation is more useful later on, but you should be comfortable with both.
Okay.
And we can talk about...
A lot of my answers on my homework, I did both just because I didn't know what...
Good. That's good to practice
And
both.
then, even so, when it did have the actual interval notation, do you still want the union symbol in between the two different sets, or can you just put the two sets?
In which notation? The interval?
Yes.
You should put the union symbol between them. Yeah. All right. So last time we were doing 3-1, right? Trying to get my notes up here. Turn my phone off. Okay. All right, so we had gotten all the way. I had left some stuff for you to do the arithmetic operations. I don't know if any of you did those, but we had stopped here at the difference quotient. I'd shown you this picture, and I believe we had done one of those. Did we do one? Okay, so that's where I want to pick up. This difference quotient idea is one of the most important algebraic ideas that we have going into calculus later, is to be able to do this difference quotient. I think I explained that to you last class. But that was so long ago, right? Since then you've had a good weekend and forgot everything? Okay.
What's your name again?
That's a great question. I don't even know. It's been that long. So the difference quotient applies to any function. So if somebody gives you a function, you can always figure out what that is. And it has a special geometric meaning. It represents this line that cuts through the graph, and I showed that to you last class, or the slope of that line. So now let's do B, because we didn't do part B. Let's take the function f of x is 1 over x cubed, and let's find the difference quotient for that function. So this is going to require some algebra. So there were 3 parts to the difference quotient. I said there's like the top left, the top right, and then the bottom, right? The bottom is always h, right? It's always going to be h, so you don't have to worry about that. The top right is always exactly the function that's given to you. The top left is the only one that requires a little bit of work. So what I'm going to do is figure out the top left first, and then I'll put this all together in this quotient. So what is f of x plus h? For this function, if I replace the x with x plus h, it becomes what? X plus h, the whole quantity cubed. That's what it becomes. What it does not become is this, all right? This is not the same thing, right? The x plus h is actually being substituted in for that x. It's not, leave the x here and just add an h on the outside. So that's one of the common mistakes that I see, is an addition of h on the outside. Understand the difference? Okay, so if that's going to be the top left, the top right's going to be this, and then divide the whole thing by h, then we're ready to actually set this up. Okay? Let's do that. And I'll do it right under here. So this quantity, the difference quotient, equals f of x plus h, which is this, 1 over x plus h cubed, minus f of x, which was 1 over x cubed, all divided by h. Yes? Now the goal of difference quotient, and keep this in mind as we work through the next few examples, the goal of the difference quotient is to try and get this h to cancel. That's what you always want to happen when you're doing difference quotient. So somehow algebraically, we really want that h to go away. And it's tied into the fact that, and again, I don't know how much of this you're going to remember from last class. It's that in calculus, what we're trying to do is find the slope of this line at a single point. So we take that blue point and we move it closer and closer to that black point until we get right on top of it. And that gives us our, what we call our tangent line. But to do that, the distance between these 2 points on the x-axis, we said that the difference between those is h. It's hard to see it in green there. But we need to make that h become very small and actually become 0. And that's a problem here. If I let h be 0 here, isn't this division by 0? But if we can get the h to cancel, then we don't have that issue. So that's the goal. Let's see if we can actually make it happen here. So whenever we have something like this, we call this a complex fraction because it's a fraction with fractions inside of it. So what we'll do is we'll try and get a common denominator between these two. We'll try and put these two together. All right? So what common denominator would I have? What's the common denominator between these two? X cubed and x plus h cubed. You have to have both of them, which means that you have to, on this fraction, you have to introduce x plus h cubed on the top and bottom. And then on the other fraction, I have to introduce what? X cubed over x cubed on the top and bottom, right? Now, if I do that, since this is multiplication between these two fractions, I just multiply straight across. X cubed times 1 is x cubed. So I have x cubed on top. The bottom is still the common denominator, x cubed times x plus h cubed, minus, now on the top over here, it's 1 times x plus h cubed, so it's this, over the common denominator again, all of this over h. Now that these have the same denominators, I can put them together. And that was the whole purpose, right? Don't do this. Don't come in here and cancel. Say, cancel the x cubes, cancel that, because you'll be right back where you started. You'll undo what you just did. So put them together now. So we'll have, I'm going to go up, because I know the camera kind of gets in the way of things. I'm going to go up here. The top is going to be the x cubed minus this numerator, x plus h cubed, all over that common denominator, x cubed times x plus h cubed, all of this over the h. Notice my division bar is bigger on this one? Remember we talked about that? Okay. All right, next step is to see if there's a way we can get that h to cancel. We still don't have anything obvious. Maybe what we can do is try and clean up this numerator. And to do that, why don't we actually expand x plus h times x plus h times x plus h? Yeah? That sound like fun? No. X plus h times x plus h times x plus h. So when we do something like that, I'm just doing this right here. When I do that, I like to do these two first. Put those two together, and then have the x plus h sitting out here waiting for the rest of this. So what would you get here? Good. X squared, xh, and then another xh, so 2xh. And then what's my last one? H squared. Just be careful. When you do this cubing, you don't cube each one, right? That's a big no-no. You have to cube the whole thing. Now at this point, how would you multiply this out? How would you do this? You do, one way you can do it, and the way I recommend, is you start with the first one, x, and you pass x through all three. Once you do that, then you come through with the h, and you pass the h through all three. So you're going to have a total of 6 multiplications here. Then collect all your like terms together. So my first one, x times x squared is x cubed. X times 2xh is 2x squared h. X times h squared is xh squared. Then I do the next one. H times x squared, I'm going to write as x squared h. H times 2xh is 2xh squared. And finally, the last term, h cubed.
Is it x squared h or x squared?
Which one?
Oh, no, it's w.
We're okay? So I'm doing x times this x cubed, 2x squared h, xh squared. H times x squared, you can write it the other way around as x squared h. And then h times 2xh is 2xh squared, that's this one. And then h times h squared is h cubed. Now collect any like terms together. So I believe this, and where is it? This go together? So I have 3 of those? 2 of them and 1 of them? Yeah? And then these 2 go together. This, and this, so I have 3 of those. So I will have, as a final result here, again, I'll put this above here so it's easier for you to see, x cubed plus 3x squared h, oh, forgot the h, plus 3xh squared plus h cubed. Whew. Okay. That's what that cubed is, right? That's what that cubed is. So now I'm going to go back to this. I'm going to rewrite that problem, but right here I'm going to replace all of this quantity with this expression right here. And also keep in mind that we have a minus sign here, don't we? Yep. So doesn't that minus sign have to distribute to each of these? Yep. Yes. All right, so I'll do that right here. So that top line is x cubed, there's x cubed, minus, now I'm subtracting each one of these. So how about minus x cubed, minus 3x squared h, minus 3xh squared, minus h cubed, all over the common denominator, all of this over h. Do you see what happens? Do y'all have any questions? Y'all are kind of looking at me.
How do we just go, how do we just clearly make it?
Okay, because there's a minus here, right?
Yes.
So if you're saying minus this entire quantity, and that entire quantity is this, then you're subtracting each term. So you could have looked at this as having a parenthesis, and then there was a minus, that one right there in front, and so that minus changes the signs of everything. Critical step, though, because if you miss that, then everything's going to be off by a sign. And you won't get what is about to happen. It won't happen if you've missed that. So do you see it? What's going to happen? What do you got?
Because I thought there was only one x cubed.
Yeah. What can I do here? What's x cubed? Take away x cubed. It's gone, right? All right. What did I say the goal was? Cancel an h. Notice that every term that's left right here has an h in it, doesn't it? On the top. Doesn't that mean I can factor an h out of the top now? So watch what I do here. I'm telling you all, this is what makes the calculus even more difficult, is the algebra involved in it. This is the algebra you run into in Calculus 1 all the time. So you have to be good with algebra in order to do it. Okay, so I'm going to take an h out of each of these. If I do that, I have an h that I'm pulling out. What do I still have here? Negative 3x squared minus 3x h minus h squared, right? That's.
Oh, never mind.
You see it? I pulled that h out. I'm pulling one of the h's out of this. I'm pulling one of the h's out of this. So one h came out of each of these. That's all still over my common denominator. I haven't touched the common denominator, right? I've just left it alone. And all of this is over h. Can those h's cancel? What do you think? Can this h and this h cancel? Well, isn't this the same as a fraction over a fraction? Isn't that the same thing, a fraction over a fraction? So isn't this a fraction divided by a fraction? And isn't that the same as multiplication of the reciprocal? So couldn't you flip that like this and really make this, what, a 1 up here and an h down here like that and make it multiplication and forget this even happened? And then that h, couldn't that h cancel with this now? Because it's all multiplication, right? It's this times that. So this h and this h go away. And what you have left is your answer. You have to write it out, though. So we have negative 3x squared minus 3xh minus h squared, all divided by our common denominator, which we'd never touched. Oh, cubed. That's it. Believe it or not, in Calculus 1, that's what you want to get to. And then what we do in Cal 1 is we say, now, let h go to 0. Let h actually smash. Let that green thing go to nothing. And that goes to 0. This whole thing goes to 0. That goes to 0. And then whatever you get, whatever you have left over, represents the slope of that tangent line at that single point. It's pretty remarkable. But that's, you have to be able to do this algebra to make the h go away. Question? Yes?
What happens if you elongated the top?
Yes?
What if you did the same with the bottom?
Nothing. You would just have it all written out here, but it wouldn't help you in the canceling of h's. The key was this part right here. So you notice that I couldn't factor an h out unless these went away. As soon as these went away, then I could actually pull an h out. So if you were to expand this out, it wouldn't really help you in any way in terms of simplification. Yeah? Okay.
Typically always the case,
What's that?
that you wouldn't have to touch the,
Usually, yeah. You usually don't have to do it. It doesn't really benefit you to do it, to touch this. But I don't want to say always, because I'm going through the Rolodex of different problems in my mind right now, trying to figure out if that would. We're going to do some more that you'll see requires more algebra. Yeah.
So that formula that you gave us at the very beginning is what you're going to use all the time?
Difference quotient is always that expression that I put in the top left at the very beginning. So
That's what we use for 1.
that's what you do for what?
1 absolute 3.
Yes. Well, no, the difference quotient is for any function. So what I did is I gave you the difference quotient, f of x plus h minus f of x over h. Now it's my job to give you a function. So I gave you 1 over x cubed. So you did the difference quotient on x, 1 over x cubed. Here's the answer. If I give you a different function, you have to set that whole thing up again and then get an answer. And I'm going to do, what, 2 or 3 more of these now? You can never get enough practice. And the algebra behind each of these is all different. And I'm going to waste some more time. I'm going to show you something that I think you might appreciate. All right, so x plus h, we did that to the 3rd power, didn't we? A second ago, and we had to multiply it all out. Okay, tell me what x plus h to the 1st power is. What's x plus h raised to the first power? Just itself, right? So I'm going to write it like this. X plus h, all right? That's what it is. What's x plus h squared? So if you did this, you know, you'd have to do your little FOIL or whatever. You would get x squared 2xh plus h squared. That's what you get, right? All right, and then we just did x plus h cubed, didn't we? And we did that. It was pretty nasty, but we got what? X cubed plus 3x squared h plus 3xh squared plus h cubed, right? That's what we got? Yes, that's right. So if we do x plus h to the 4th, that's x plus h times x plus h times x plus h times x plus h. One more, sorry. It would be x to the 4th plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the fourth. Of course, right? That's what it would be. So now you're lost, right? Maybe not. What would the next one be? X to the fifth plus 5x to the fourth h plus 10x to the third h squared plus 10x squared h cubed plus 5x h to the fourth plus h to the fifth. So I'm just showing off now, right? No, there's something's going on here, right? You see the pattern? Does anyone see the pattern? There's a pattern. It's Pascal's triangle. You've seen that. Interesting. Where did you see that? Where did you see it? Where have you seen Pascal's triangle? High school? Okay, pre-cal and cal. Good. Okay. So Pascal's triangle. But let's see if we can identify the pattern here. Just look at the variables only. Don't look at all the numbers like the 3 and the 6 and the 10. Just look at the variables. Okay, if I have the first power, right, then I start with x to the first power and h to the what power? There's no h here. So 0 power. And then on the next one, what's the power on x here? 0, and what's the power on h? 1. So you could look at it this way. Started with x to the first, h to the 0. And then in the next line, the power of x came down, the power of h went up, didn't it? That's the same thing that happens here. Start with x squared. How about h's? There's no h's. Next line, I have x to the first power, and now h appears, right? H to the first power. Next line, x power comes down. I don't have an x. H power goes up again. And that's what's happening in all these lines. The powers of x are going down as the powers of h's are coming up. Do you see it? So let's look at the next line, x plus h to the sixth. Don't worry about the numbers right now. Just tell me the x powers. What would I have? X to the sixth plus, I would have some number in here. I don't know what it is. Then x to the fifth h. And then plus, what would the next one be? X to the fourth h squared. The next one would be x to the third h cubed. And then the next one would be x squared h to the fourth. And then the next one, x h to the fifth. And then finally, h to the sixth. Do you all see that? All you have to do now is figure out what the numbers are. And that comes from something called Pascal's triangle. It's named after a mathematician named Pascal, but it's actually a ripoff. The Chinese had found it a long time before Pascal found it. But let me show you Pascal's triangle now. I'm going to do it on the side. It's not going to be on camera. Pascal's triangle works like this. You start with a 1 at the top of the triangle. And then what you do is, the rule is that the edges always have to be 1s. So the next line is going to have 2 numbers in it. This one had 1 number. This one has 2. And if both edges have to be 1s, then that's the only choice I have. The next line is going to have 3 numbers in it. And the edges have to be 1s. So that means I have to figure out what this middle number is. And it's going to be these 2 added together. That's 2. Now the next line is going to have how many numbers in it? 4. The 2 edges have to be 1s. And I have 2 more numbers to fill in here, right? But if I add these 2, I get what? 3. These 2, I get 3. Do you see the Pascal's triangle in this over here? Okay, so the first one is up here, 1. The number in front here is 1 and 1. Then we have 1, 2, 1. See it? Then we have 1, 3, 3, 1. The next one is what? 1, 4, right? That would have been 1s on the edges. 4. What's the next number? 6, 4, 1. You see it? So you want to fill this in for me then? You know the edge is 1, right? What is the next number going to be? 6. Because it's this 1 and this 5 together. What's the next number? 15. What's the next number? 20. The next number? 15, 6, 1.
18 plus X. Yeah.
Do what?
The 15 needs to go in.
Oh, yeah. 15 goes right here. Thank you.
I have a question.
Yes.
You said
Yes.
Or they go down in the backup, but on
The x's go down, the h's come up.
the, okay.
So x, look at just look at x here. 6th, 5th, 4th, 3rd, 2nd, 1st, gone.
Okay, that's where.
Right?
Okay.
5th, 4th, 3rd, 2nd, 1st, gone. And then h's are opposite, right? Gone, h squared, h cubed, h to the 4th. Anyways, this is just something that may come into play later on. I know for a fact in Cal 1, what we do is we say, well, what would this look like? What would x plus h to the n power look like? If I don't tell you what the power is. So what can you tell me the first thing would be? X to the n. Plus, now do you know what the number is that goes in front? There's a pattern. Look at these numbers, right? Look at third power, what was that second number? 3. Fourth power, what was the second number? 4. Fifth power, 5. Sixth power, 6. Nth power, n. And then what's the power on x going to be now? But 1 less, right? It's going to need to come down. How about n minus 1? And what's your power on h? H to the first power. Do you agree? And then the next one, I don't know what the number would be. Okay, it's not easy. I mean, it can be done, but what would the power on x be? n minus 2. And h would be squared. And you could continue this all the way till you get to the end. What would the very last one be? H to the n. So in Cal 1, this is what you look at. And then you do something kind of interesting with that. But you need to know how to expand that out. And that the way to get this is to use this idea of Pascal's triangle to be able to recover that sort of information. All right? Sorry, off topic a little bit. All right, back to difference quotient. Give you a different function here. I'm going to change it. I don't even like any of the ones I gave you there. Y'all seem to want, it looks like you want something kind of more difficult, no? You want to be exposed to something more difficult? All right. I'll do 2 more. This one won't be the hardest. The next one will be the hardest. There's the function. It's a square root function. Find the difference quotient. You have to find f of x plus h minus f of x all over h. Right? That's what the difference quotient is. Those 3 pieces. So find the difference. I called it difference quotient, right? DQ last time. Everyone started wanted to get a blizzard after I said DQ. So the part of it that you really need, right, the part that's always going to be a little bit troublesome is that part, right? The top left of the difference quotient. So what is f of x plus h? X plus h minus 2. Right? That's what f of x plus h is. You're replacing the x here with x plus h. Again, what it is not is this. It's not that. That's just you giving me f of x and then throwing an h on the outside. You're not doing that. You're adding the h inside the function with the x. No, you wouldn't need it in parentheses because if the parentheses were here, it wouldn't change anything here. Because it's still whatever this quantity is minus 2. Right? That's not multiplication, so you don't have to distribute. Well, that's not so bad. I guess it's not so bad. Let's write the difference quotient down. Top left is what? Square root x plus h minus 2. Then minus, we're supposed to put f of x here now, right? What is f of x? Square root of x minus 2. All of this divided by h. That is the difference quotient. But to be done, you have to get the h to cancel. So how in the world are you going to get an h out of there? How you can get an h to cancel? The only h you have is trapped inside of this square root, right? You can't just pull this thing out.
Just raise everything to the second power.
Good proposition. What do y'all think about that? Square it.
Isn't it supposed to be the reciprocal? X plus h minus 2 plus x minus 2 on this side?
That's called the conjugate, but yes, that's another idea. Okay, so let's resolve the first one, okay? Can we just square this to get rid of the square roots? What do you think? Yeah? Okay, so this is a fundamental thing when it comes to algebra and expressions. Let's say that I have an expression here, 4, right? There it is. If you come in here and you square it, is it the same thing? No, it's 16 now, isn't it? So you've changed the problem when you squared it. That is different than this. Now let me write this down. X is 2. Now can you square both sides? Yes, and you get x squared is 4. Now you still maintain some of the equality here. You know that 2 does work, right? So even though you've changed the look of the equation, it's still valid. But when you just take an arbitrary expression like 4 and square it, it's no longer the same expression. So you cannot do that. You cannot just take an expression and square it just because you want to get rid of square roots. You can do that with an equation, you can, but not just with something sitting there staring at you in your face. Understand the difference?
Can you set it equal to 0?
You could, not equal to 0. You could set it equal to y and square both sides, but then you're going to have to go back and get y back eventually. It's not going to save you. It's not going to save you, trust me. So that was the first proposition. So let's rule that out. Don't ever do that on tests. Don't just square things arbitrarily. The other recommendation was to use the conjugate. Now the conjugate is when you have square roots. You look at the square roots, and you multiply by exactly what you see, but you change the sign between them. You remember this? Haven't we talked about conjugates? I know it was part of your homework at some point. Make sure it's coming out. Boy, that's not coming out on my video. Just going to move this a little bit. I think someone sabotaged my camera while I wasn't looking. Okay, this is the conjugate. Now, why do I put the conjugate over the conjugate? Why do I put it over itself? Because it has to be a 1. You can't just come in here with a conjugate on top and not, I mean, that would be like squaring it. You can't do that. But you can always multiply something by 1. Now, why is it that the conjugate is going to be our choice? What is the effect of the conjugate up here? The square root's going to go away. That's what we want. So we come in here, I multiply this times this. They're exactly the same thing. So you're squaring a square root, and it goes away. So you have x plus h minus 2. And then what about the middle ones? What about the next two multiplications, which would be this one and this one? What can you tell me about those? This is why we use the conjugate.
They become 0.
They cancel each other out. Because this times this, right? Those two square roots are different. You would just have those two square roots. But then you have minus the same two square roots being multiplied. So they're opposite in sign, but they're exactly the same thing. So the middle two terms are going to cancel, so we don't even need to write them. Alyssa, you're okay with that? All right. That's the whole reason we use the conjugate, because the middle terms will go away. What about the last multiplication, though? This one times this one. Same roots, right? So it just goes away. So you just have x minus 2. Yeah? But what about the negative? So it's going to be minus x minus 2. Be very careful with that. That's the top. What's the bottom? So on this, I wouldn't multiply those out. Like I would just leave the h down there. Don't try and put the h through here, because remember, you want the h to cancel, so don't go mixing it up with a bunch of other crap. Just leave it over here. And then with the conjugate that's down there with it, put it in parentheses. Like that. All right, so that's the same thing. It's all of this times h. There it is. And then the top all became that thing. Anything good going to happen there? You can cancel a lot of stuff out here, watch. Now you can't cancel this h yet, right? You have to first do some algebra. This expression becomes minus x plus 2, doesn't it? And now the x's and the 2's cancel, right? X take away x, negative 2 plus 2. The only thing left up there is h. And now at this point, you'll be able to cancel that h. I think I'll do this over here. So that equals, so this equals just an h on top, the h on the bottom, then everything in that parentheses. When these h's cancel, what's still left on top? A 1. Don't forget about the 1 on top. So our final result is this. There we go. That's the difference quotient. We could go all day long on these because there's so much algebra. What? I know. This has very, very significant meaning to us, though, in calculus. Yes?
I'm confused on how you got the h by itself on top.
Okay, so this x, okay, let me rewrite this whole line. It's x plus h minus 2 minus x plus 2. So this x minus x is gone, and this negative 2 plus 2 is gone. Yeah, so it just cancels out. All right. I think that's okay. We'll leave it at that, all right? We'll leave it at that. Just be ready, though, in Calculus 1, this is going to be the mid-level sort of problem. The functions get a little more complicated, so the difference quotients get a little more complicated, and then the algebra becomes more complicated. So just be ready. It'll ratchet up a little bit in Cal 1. All right, we're going to move on, though. We need to get out of this section. So let's begin the next section, which is 3.2. And a lot of this, I think I can show you up on the notes. So let's bring this up here. All right. I'm going to blow this up. I hate just talking in almost like a PowerPoint. I hate doing lectures like that. But there's so much of this that's visual that I think we will. So please pay attention to what's up there and ask questions if you have any. So if someone actually gives you a function, like the one we just did, square root of x minus 2, the graph of it are all the points, all the ordered pairs which satisfy the function equation. Usually we graph this on a two-dimensional sheet of paper called, what do we call it? The Euclidean Plane. That's what it's called. A flat sheet of paper is called the Euclidean Plane. We can also call it R2. R2 is two-dimensional space. Have y'all ever heard R3 before? It's three-dimensional space. So when you're dealing with things in R2, you're talking about flat sheets of paper. Dealing with things in R3, you're talking about like a room. If you're dealing with things like R1, that's like the length of something. So for one-dimensional space, two-dimensional space, three-dimensional space. So here's an example of a graph. You have y equals x squared. So the graph of this function is every x and every y which satisfy this equation. So if I plug in negative 3 for x, when you square negative 3, you get 9, right? So the output is 9, the input is negative 3. We already know this, like we've seen this before, right? What I'm trying to get you to see all to see is that the graph of a function is just a way of representing all the answers to an equation. That's all it is. And so if you're able to fill in every possible value of x, you would get this blue graph. There's an easy way to determine whether or not a graph is a function. Remember we talked about functions had to have one input, couldn't have two output. I mean, one input went to one output, couldn't have two outputs. Very easy way to check that if you have a picture is the vertical line test. The vertical line test says that if any vertical line ever hits your graph more than one time, it is not a function of x. And this is the one thing that most students get right every single time on a test or a quiz. Determine if these are functions or not. So look at this one right here. Is this a function of x? Yes, because any vertical line I draw will only hit the graph one time, right? Is this a function of x? Correct, because if I draw this line, let's say right there, I'll hit it twice. And in fact, there's a bunch that if I did it, I would hit twice. What about this line over here that I draw? Do I hit it more than once? No, so that's okay, but see, the vertical line test says any vertical line I draw hits more than once, it's over. So I would be drawing, I'd be like, no problem, until I got over here, and then I would have a problem. How about this? Is this a function of x? No, same thing. Over here, draw a vertical line, we hit it more than once. This a function of x? Yes, it appears so. All right, so very simple to tell with the vertical line test if you're looking at a function. All right, the graph of a function is a fountain. You like that? A fountain of information. So you just imagine this information just like pouring out of the graph, right? There's so much stuff there that we can tell if we have a picture. Some of the things are things like this. We can determine the values of the function at specific points. We can determine where the function is positive, where the function is negative, and where it's 0. So when you say where is a function positive, we mean where is it above the x-axis. If we say where is it negative, we're saying where is it below the x-axis. If we say where is the function 0, we're talking about where it hits the x-axis. We can also talk about where it hits the y-axis. We can also talk about the domain, the range. So here's an example. I'm going to blow this up a little bit bigger. And I think for this one, I will, I don't want to have to reproduce that. So I'm going to turn my camera, make sure I don't get any of you on camera because probably, some of you are probably wanted. Got a couple of warrants. Yeah. Oh, I already know about you. I've already called in DPS on you. I don't even know if that's coming out on camera or not. Okay, well, I'm going to go over there and work this problem. So, does everyone have the questions? Because I have questions for these listed. Are y'all printing out your notes or not? Yeah? Okay. I'll write down the questions on the side. But you also start bringing your notes because it's kind of a useless thing for me to have these for you if you're not going to bring them or use them. Okay, so for this example, part A, we want to find f of -4. All right, so I'm going to call on people here. You'll have to turn your name things around so I can see you. And we'll just start right here with Kayla, right? I'll give you a minute to take a look. F of -4. So what do you think? This is saying what's the f of the number is the output, isn't it? It's the y value. So this is saying what's the y value when your x value is -4? You see it, Caleb? Take a guess at it.
Wait, well, your y value?
Okay, go to your x value of -4.
Right there.
Right here? What's your y value there? Did I count right? 1, 2, 3, 4. Okay, what's your y value there for your function? 2, right? 2. So at -4, you're up at 2. Yes? So by just looking at that function, I can tell you that for this particular function, if you plug -4 in, it spits out 2, right? I can do that for a lot of values I could tell. How about this one? What's f of -1? And let's go with someone else. Giovanna, I haven't said your name in a while. What's f of -1? 1. Everyone see that? All right. Let's ask Michael. This isn't on here. I'm making up my own now. Sorry. Michael, what's f of 1? You got the hard one, Michael. So you're going out to 1, you're looking up here, but it's an open circle. What does that mean? There's no point there. And there's no point here, which means it's non-existent. So we say undefined. F of 1 would be undefined. Everyone understand that? And you don't say equals undefined because you usually say equals a number. So f of 1 is just undefined. All right? Okay, let's see here. Who's feeling good today? Who wants C? Part C is asking, where is f positive? Where is f positive? So who wants to tell me what that even means? Why is this thing shaking so much? I'm getting nauseous looking at it. Right, it's nervous. It doesn't like. Go ahead. What was your name again? Because you don't have Liz. That's right.
I'm gonna lose it if it means me.
Okay.
F being positive meaning like where is the y value positive when F
Where's the y value positive? So anywhere where the graph is above the x-axis would be positive. So can you kind of explain to me where it's happening?
x is equal to -5, -4.
Like everywhere over here, right?
-1. No, not everywhere. I mean,
What about here? Is it positive right there?
yes.
Is it positive right here? Right there? Right there. Stop shaking. There, 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 there. Right? All of these, right? Everywhere over here it's positive y values. So somehow I need to be able to say everything over here. And actually it looks like it stops. Sorry. That's a dot. It stops. I would need an arrow to imply that it keeps going. So I need everything over there, right? How do I say that? What sort of notation do I use? Interval notation. So how do I say everything from here to here, but not that point, right? Why do I say not at that point?
Wait, yes.
Bracket.
It's closed.
It's closed, but is it positive there? It's 0. 0 is not positive. So we have to be kind of careful here. Does that make sense? So what? 1, 2, 3, 4, 5. So -5 all the way to where? -3? Okay, so let me write that down. It's -5 to -3. It is positive at -5, isn't it? But it is not positive at -3. So that would be the interval where it's positive. Does that make sense? Is that the only place it's positive? Okay, so let's get a different volunteer. Aaron, you want to go for it? Where else is it positive, Aaron? It's hard to see it, but take a guess. -1.5? Y'all see that? From there to where? 0. Okay, so how about I say what? Union, and then -0.5, you said to 0. Now, do I include -0.5 or not? No, because at -0.5, it's on the x-axis. That's 0, right? Oh, it's -1.5, sorry. -3/2, that's the same thing. Yeah, -3/2. What? Is that, no, y'all don't like that?
It's fine.
Okay, all right. Sorry, we said -0.5. This is -0.5. It's actually -1.5. This is -1.5. What? Why are you shaking your head? You just don't like that fraction? Is that all? Okay. All right, you can put -1.5. All right, do I include that or not? No. How about 0? No. Okay. Am I done? No. Union again? Where else does it pick up? Who else? Angie? You want to try it? We've taken care of this positive part, this positive part. So what else is positive here? From where to where? So if I go, how about right here? Am I positive here? I'm down here, right? So that's negative. So I can't, it doesn't start till I get to where? 1. And from 1, I'm positive until I get to where? 3. But at 3, I'm 0. So how do I say this? Union, I got another one of these. 1 to 3. Why am I not including 1? Why am I not bracketing 1? You're not even defined at 1, right? Your function wasn't even defined at 1, so you cannot possibly throw that into your answer. It can never be there. All right, is there more? Yep, from where? From 3 forever.
Is 4 a dot or no?
No, this is an arrow here. Is that what you're doing?
4 on 4.
Oh, yeah, that's a dot. Yeah, I guess so, yeah. But it doesn't matter as far as what our interval is. It's from 3 to infinity, forever. And you always put the parenthesis on infinity. So keep in mind here, when we're saying where's the function positive, these are all these intervals, these are all x values, right? Just keep that in mind. Even though we actually look at the y value to tell where we are, our answers are always off the x-axis, right? They're always the intervals of x that give us positive values out. So if I take any number in here, any number in here, any number in here, any number in here, any number, plug it into the function, I promise you it's positive. Where? Here?
Yeah.
Okay, if 3 was bracketed, that would mean I'm telling you that at 3, it's positive. What's the value at 3? 0, and 0 is not positive. Unfortunately, because if it was, then I wouldn't have even had to have stopped. I could have gone from 1 to infinity. Like if it just came down here and just looped like this, then I would have never had to stop. I could have gone from 1 to infinity. 3 wouldn't have ever come into play. All right, that makes sense? All right, so what about where it's negative? It's the opposite question, right? Where is it negative? Everywhere else. Well, not necessarily, because some places it's 0. So part D, where is negative? I'm going to write this a little bit different. Instead of writing the word negative, I'm going to say, where's f of x less than 0? Doesn't that mean where's f of x negative? I could have done the same thing over here, and I could have said, where's f of x what? Greater than 0, right? Okay, so where's f of x? Who's up? Let's see. Jordan? We haven't heard from Jordan. No, we did hear from Jordan. You helped us with the conjugate. Chris?
Sure, all right.
Negative?
So we got -3
Okay.
to -1/2.
Okay. So -3 to -1.5, 1.5. Is that all right with you?
Yeah.
Since y'all didn't like the 3 halves. What do you want me to do parenthesis-wise?
Or I'm sorry, parentheses on both sides.
Parentheses on both.
Then we could do a union.
Union?
Yes. 0 to 1.
0 to 1.
Both with
Parentheses on both.
and I call it
Yeah, that looks good. So between -3 and -1.5, we're below the x-axis, but not at the actual endpoint. So that's why we didn't put brackets on them. And then from 0 to 1, right here, we're below the x-axis. Other than that, we're not. Make sense? Okay. All right, part E is saying, where is f equal to 0? So where is the function actually equal to 0? So we're going to ask someone else now. Where is f of x equal to 0? And you want to go?
Yeah.
Lilius?
Yes.
Okay.
X equals -3,
Okay, x is -3,
-1.5,
-1.5,
0,
0, and 3. So we're picking off the x values where the function was actually 0, which was here, 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 and here, right? Those 3 values, or those 4 values. So you just listed them out, x equals this, this, this. So this is different than an interval, isn't it? So whenever we have a list of numbers, we don't use interval notation. We use like this. We can use a set of braces, and list the numbers out.
Would you put X so that X equals?
You could say X, remember that symbol? X is an element of this set. This is a set of numbers as opposed to an interval. The difference is you use the braces instead of parentheses. Okay? All right, so far, see, there's a fountain of information coming off of this graph. Part F. What's the domain? Dom F. What's the domain of the function? So the domain is where the function is actually defined. And what we're doing is we're looking at all the x values that have a y value that corresponds with it. So remember, to be in the domain, there has to be an output. So I'm looking along the x-axis and I'm saying, which x values do actually have something come out? So how about way over here at like -10? Does anything come out of the function? No. So I'm kind of like coming out here and I'm looking up and down. I'm saying, do I hit the function or not? Nothing, right? Not till I get to where? -5. As soon as I get to -5, I'm hitting stuff, right? Until I'm hitting until I get to where? 1, and then at 1 there's nothing. What about after 1? Still going until when? Forever. So I need to be able to say that. Starts at -5. Let's see. Jasleen, hello. You want to do it?
Sure.
Okay, so start me off.
So, -5.
-5.
Do we do the less than or equal, or the bigger than?
Let's do an interval. Let's do, so like comma, and then how far do you want me to go?
Infinity.
What about, remember we had a little issue at 1, remember? Right, so we need to stop there. And we need to say from -5 to 1, we've got function. Do you have function at -5? Yes, so I need to put a bracket. Do we have function at 1? No. Now, continue.
And then
1 to infinity. Union, 1 to infinity. That's your domain. The next thing is the range. The range is a little more confusing. We call this RANF, range F. Go for it again. Can you explain what the range is, like in terms of like what?
The range is like all the y values and what, like where they show up in the graph. But like I was asking because I don't know
Okay.
for sure if like the closed circle will cancel out the open circle and it'll be a bracket anyway.
If it exists, if that y value is ever achieved, then you count it.
Cool.
So
So isn't it just -1 to infinity because that keeps going up and out?
yes. So with range, instead of looking up and down and looking for a function, you're going left and right and looking for a function. So I'm moving along the y-axis, start at the bottom, and I come up. Am I hitting anything? If I look left and right, do I get any graph this way? Not until I get to where? -1. At -1, I go out this way, I hit graph. And that's all I'm looking for is graph. So at -1, I start. And then as I move up and look left and right, I'm hitting it a bunch, right? Both directions? Okay, we got a circle here at 2, but look, over here I do hit.
So infinity.
So, and as I keep going up, over here at 4, I don't hit this direction, but this arrow implied that that kept going. So I would hit it over here somewhere to the right. So it looks like everything from -1 up forever. So I write -1 to infinity, always a parentheses here. We did achieve this, right? But y is an element of this. See, these are y values. This is, so far with what we've looked at, that's the only one that has actually been a y value. The range always tells you the y's coming out of the function, as opposed to domain where it tells you the x is where the function's defined.
I don't know if you'll do it later, but how do you get the range from like if you just gave us a function, not a graph?
That's more complicated. Getting the range of a function is one of the